Okay, on to integrals now. Integrals are the area under a curve, just like we were doing. Before we were estimating, but there are ways with calculus to find exact area, especially under curves, that you had to just estimate, like using boxes, just like before. So, for example, you have f of x, and we want to find the area of this curve that's changing at every single point. And we want to find the area from a to b. This area right here is the integral. And we write it like this: a to b of f of x dx. So this is just giving our boundaries. F of x is the curve that we are getting the area under, and dx just means that we're going along the x-axis as we do it. Okay, one thing to note, a few things to note here. The area could be negative. What in the world does a negative area mean? Well, let's say we have a curve like this. If we find the area from A to B, you have area above. So this is all going to be positive green area. As you start moving from B over to C, that curve is actually underneath. And so when you do integrals, when you do what we're about to do, you consider area that's under the x-axis as negative. And then the area that's above the x-axis is positive. So in this particular example up here, if the area that's green is equal to the area that's red, and you do the integral from A to C, the areas would cancel each other out. And so you're going to see area cancel itself out. Okay, so just to get used to this notation, we're going to do something like this. Now, the function is 2, which means if you were to graph this, you have a curve that doesn't curve at all. It's really just a straight line. It's y equals 2. We're doing this from 1 to 5, so from 1 to 5, and we want to find the area underneath that curve. That's what this whole integral means. And so to begin with, we're actually just going to be doing a few problems where you can draw a picture of the graph, and you don't need to know the calculus way to do it. You can just figure it out by visually looking at it. So this is a rectangle that is 4 wide. It's also 2 tall, so the answer to this is just 8. And so that's one example where if you just know the picture, can graph it, you can figure out the area simply by doing that. Another example where this will happen is something like 2x plus 1. Let's say we wanted to do the integral from 0 to 2 of 2x plus 1 dx. Well, drawing a picture this way, we have an y-intercept of 1, and every time you go over 1, you go up 2, over 1, up 2, just drawing a graph of what that would look like. It's just a line. Now, I actually want to find the area from 0 to 2. I want to find this area underneath the curve. There's a couple ways you can do it. I think I just prefer to chop it right here. Think of this as a rectangle, and then think of this triangle, and just combine the areas. So the area downstairs is going to be a 2 by 1, so that's 2 units squared. The top is going to be 2 across, but then 1, 2, 3, 4 tall. So to find the area of a triangle, you do length times height, and you cut it in half. That would be 2 times 4 is 8. 8 divided by 2 is 4. So the total area here, we would just calculate to be 6. Okay, so you might be wondering, when it's not that easy, when it's not a nice straight line, how do we find the area? And so this is what we're going to start getting into. This is extremely important. It's called the Fundamental Theorem of Calculus Part 2. And I've decided that we'll start using it and getting used to it, and then next session, we'll come together and I'll try to explain where this comes from. If you want to find the area of this, this is what you calculate. Now, it's important that you understand what that big F is in relation to the little f. The big F is what's called the antiderivative. What that means is that if you were to do the derivative of f, you would get little f. And so this is where we have to start thinking in terms of derivatives in calculus. They're going to give you an f, and you have to go backwards to figure out what would give you f as a derivative if you were to do the derivative on it. So what we're going to do first is we're just going to talk about a few antiderivatives. And then later we're going to come back to this in the next video to figure out how to use that for area. So let's look at these examples down here. Like this is telling us to do an antiderivative. If this is little f, we want to get big F. So what if you did the derivative to it would give you x? We're going backwards now. So if you think about it, we would have to have x squared, because part of the power rule is that you decrease the power by 1, and if that happened here, this would be 1. So that matches up. But another thing to consider, if you were to derive x squared right now, you would not only lower the power, but you would also multiply by the power. So it would be 2 times. Now we don't have a 2 in front of here. So if I put a 1/2 in front, it would cancel out. So think about it. If I was to do the derivative of this, I would bring the 2 down. 2 times 1/2 is just 1. And then we'd lower the power to get 1. Okay? So again, I don't have numbers here, so this is just finding the antiderivative. In this case, it's the same thing. A higher power of x would be x squared. A higher power here would just be x, and I could put a 5 here. And now, the reason I can just put a 5 here is because if you think about the derivative of 5x, derivative of 5x is 5. So that's okay. Now, if I multiply by 2, I would get just a plain x. So what number has to be here so that if I multiply by 2, I would come out to have 3? And that would be 3/2 or 1.5. So now if I think about this being derived, 2 times 3/2 is 3. You lower the power to get 1, and that's going to be your derivative. Now one thing to note here, before I show you some more antiderivatives, you should always put something outside your answer called plus c. It's the constant. And this is not too hard to understand. If you just look at this example of like x squared plus 1 and x squared plus 7. Now if you do the derivative on this side, you're doing dx, then you would just get 2x. Over here you would just get 2x. So one thing to keep in mind is that when you do a derivative, you actually lose information back here. There was a number that just dropped when you did a derivative. So if we were to go back and we want to go a level up, we recognize there's always going to be a number that was dropped. And so we put a plus c at the end. Alright, so I'm going to give you one to try. We're going to find the derivative of x squared plus x to the 4th dx. Alright, you should pause the video, give it a try. What derived would get you what's in those parentheses? Alright, so in this case, we would take x and raise the power, and then we would think 3 times what would give me the power back here. So 3 times 1/3 would cancel out to be 1. And double checking, if I lower the power, I would get x squared. So same thing over here. If I raise the power to 5 here, I've raised the power up 1, but I have to think, if I derived it, I would have to multiply by 5, so there should be a 1/5. So taking the derivative of this, we multiply by 5, it turns into 1, and then we just have x to the 4th. And don't forget the plus c. Alright, so there are a few other ones that you should know now, because it's just backwards deriving. Like, for example, the derivative of cosine x dx. Well, think of the derivative tower. Negative sine, negative cosine. This way is d dx, so this way is integrating. Finding the antiderivative. So if we are already at cosine and we want to do the antiderivative, we go up to sine of x, and then write a plus c. Okay? And one that you should remember, if you didn't remember this already, I mean, you should remember it now, is that secant squared is actually the derivative of tangent of x. So when we do the antiderivative, we would write tangent of x for our answer here. Some other important ones, the integral of 1 over x dx. What function, their derivative, which one of them is 1 over x when you derive it? That is the ln of x. Okay, and one thing you should know about this, and this is getting really nitpicky, is that the ln of x only has a domain over here, meaning it only exists over here. But if you look at 1 over x exists on both sides. And so what happens here is the absolute value is telling us that the ln should work on both sides. So the takeaway is, if you don't understand that much, you can at least say that whenever you do the antiderivative, instead of a parenthesis, do absolute values right there. Okay, so that's 1 over x. One other one that's very important is e to the x dx. So think of this, what derived will give you e to the x? Well, that's just itself. And then the derivative will have, the antiderivative will have a plus c.